Section 3.8 is on page 247, talks about inverse functions. We start off by defining what a one-to-one function is. So we're reading what's in the blue. A function is one-to-one, and we write 1-1 instead of writing the whole three words. Excuse me. So a function, it has to be a function satisfying that the first coordinate does not repeat if the second coordinate does not repeat. So domain and range are the same. I look at an example. Determine if the following relation is a one-to-one function. So it is a function. That's good. Is it one-to-one? Does the y repeat? The y doesn't repeat. We say yes. This relation is one-to-one. And if I look at part B, we say, okay, 1, 2, 3, 4. Very good. That's a function. 2, 3, 4, 3. Wait a minute. Those are the same. This is not one-to-one. It is a function, but it's not one-to-one. If I do this graphically, if I look at the graph of the first coordinates, 1, 2, 1, 1, 2, 2, 3, 2, 1, 2, 3, 4, 4, and 5, -1. I already know that those satisfy the vertical line test, meaning each vertical line crosses its graph only once. If I look at part B and sketch it, I'll come back to A. 1, 2, 2, 3, 3, 4, and 4, 3. Well, I notice this also satisfies the vertical line test. That's not a problem. Well, keep in mind, we did a vertical line test when we said that the x coordinate doesn't repeat and x equal a number is a vertical line. Now that we're saying we want to check if y does not repeat, y equal a number is a horizontal line. So we notice here a horizontal line crosses once. That was one-to-one. But here, if I was to go ahead and put a horizontal line through those, I do notice that that horizontal line crosses twice, and that's not a function. And that's where the horizontal line test comes from. We say a function is one-to-one, so it must be a function. It is one-to-one if no horizontal line intersects this graph more than once. And we define the title for this section, inverse. That's how we write inverse. This is with f inverse of x, the inverse of a one-to-one function. For you to find an inverse, the function must be one-to-one. So, if a function is one-to-one, it has an inverse. If a relation is not one-to-one, it can't have an inverse. The inverse of a one-to-one function is a relation that interchanges the coordinates. All what it does, it swaps the coordinates. And let me get you an example. So the next set of problems, we're still checking this one-to-one correspondence. We did with points. Now we're doing that with graphs. So if I glance at 7 through 12, it says, use the horizontal line test to determine whether each function is one-to-one with an inverse. So checking if it's one-to-one. You'll notice if I draw a horizontal line right there, that crosses more than once. This is not one-to-one. It is a function because it satisfies the vertical line test, but it's not one-to-one, therefore an inverse does not exist. Because here we're restricting the inverse of a one-to-one relation. Number 10, if I draw horizontal lines, you'll notice there's nowhere I could draw a horizontal line that will cross the graph of this function more than once. Therefore we say yes, this is one-to-one, which means an inverse exists. And if I take number 12 and put a number line or horizontal line right there, again, you're only looking for one exception. This is not one-to-one, which means an inverse to this relation does not exist. Now let's talk about an inverse and break that down. An inverse is a relation that interchanges the coordinates. it really swaps x and y to y and x. And let me do some examples really quick. And here's our first example. Find the inverse of the following one-to-one function. This is one-to-one because x does not repeat, it's a function, and y does not repeat, which is the second coordinate. If we call this relation f, we say, look, the inverse can be determined by, and how does that work? You switch the x with the y. If the original is one-to-one, then the inverse must be one-to-one as well. Now let's reinforce that idea again. Here it says, evaluate, if possible. Given P and Q are inverses, this is what they're saying. The best way is to do this the most basic setup. In P and Q are inverses, so we know the x and the y swap. When they say P of 9 equal negative 4, that says when x equal 9 in the P function, y equal negative 4. If I switch those to the inverse, doesn't that become negative 4, 9? And what is this asking? This is asking what's the y value in the inverse when x equal negative 4? What's the y value? Doesn't that mean Q of negative 4 equal a 9? Let's do it again. Here, we're looking at Q is given, but we know Q and P are inverses. So if I look at Q, whatever x and y are, they're going to switch. I look at Q, when x equal 2 in Q, Q of 2, that's the y, is negative 7. So automatically, when those switch, that's a negative 7, that's a 2. And I realize that, wait a minute, this is saying, what does y equal when x equals negative 7? Well, it equals a 2. And if I get to the last problem, or the last example I have, again, here's P. In P, when x equal 1.8, P of a value is the y value, that's a half. In Q, that's going to switch. And that's going to become 0.5, 1.8. This says, find me the y value when x equals 1.8, but I have x equals 0.5. I know Q of 0.5 equal 1.8. That's all I can get. What does Q of 1.8 equal? Not a clue. There's no way of figuring this out. Now, in 23 and 24, well, there's only one problem, so I added an example. Graph the inverse function of each relation. Actually, I'm going to get one more example when I'm done with this. Well, let's see how that works. So, given points, we know how to find the inverse. We switch x with y. Very easy. Given a graph, we're going to do the same. We're going to look at the graph, say, okay, you know what? Switch x with y. What do you think that point is? That's 2, 0. So, switch x with y, that becomes 0, 2. Let's pick a point. This looks like it's 1, negative 1. So, negative 1, 1. And this point looks like 3, 1. So, 1, 1, 2, 3. And that's how the inverse looks like. The example I gave is 1-to-1, so if you want to sketch the inverse, well, take the point negative 2, 0, switch x with y, that's 0, negative 2. This point looks like negative 1, 1, so switch x with y, negative 1, 1, 1, negative 1, got it. And if I pick this point, looks like this point is 2, 2. If I switch x with y, that's 2, 2. That's the graph of the inverse. I'll say this is the inverse of x. This is the inverse of x. And I'm going to get one more graph and elaborate on this just a bit. This is on page 253, with all the excitement, I forgot to give you a page. So I added one more example, and it's right there. If I wanted to sketch the graph of the inverse, I would switch x with y. This point is 0, 2, 2, 0 will be a point, and this point looks like 1, negative 1. So negative 1, 1. Connect those with a straight edge. And there it is. It turns out, if you really look closely, a graph of f and its inverse are symmetric with respect to the line y equal x. It turns out that's how it works. If you draw the line y equal x, that line should literally be a mirror image of folding the page above that line, and the red and the green will overlap. If I was given an equation, the same deal will happen. And the definition, this is our last definition. It says if two functions f and g are inverses, then if you take their composition, the g composite f, you should get x, and you have to do both. F composite g of x equal x. This is really important. The domain of f must equal the range of g. The domain of g must equal the range of f. Remember, if f and g are inverses, if we say this is xy, in the inverse, that's going to be yx. The domain of the original is really the range of the inverse, and the domain of the inverse is the range of the original. So, when they ask here, find the inverse function of each function if it exists. This is 1 to 1 because we know that's a straight line. So how do you find an inverse? We said we switch x with y. And if I solve for y, subtract 5 from both sides, and y would equal 2x minus 5 over 7, and we label that as an inverse, indicating this 2x minus 5 all over 7 is the inverse of this relation. When I look at number 28, that's also a straight line. I know that's 1 to 1. The only straight line that's not 1 to 1 or doesn't have an inverse would be a horizontal line, or vertical line for that matter. So this is 1 to 1. What I do, I switch x with y, clear the fractions, solve for y, and I could divide the whole thing. I could divide those individually. It makes no difference. And I label that as my inverse. And that's how it works. 32 is a bit trickier in the sense I say, okay, well, I could do this. This is 1 to 1. I know that. I know that from the graph. Y equal, switch x with y. Well, how do you solve for y? Square both sides. Move the 6 over. And divide by 3. But then you go, wait a minute. I can't label that as an inverse. And why is that? That's not 1 to 1. If I look at the graph of the original, notice how it goes. The graph of the original, the domain, 3x minus 6 must be bigger than or equal to 0, right? So 3x must be bigger than or equal to 6. X must be bigger than or equal to 2. So, anytime you're stuck on a problem in math, graph it. We're going to pick 2. If I put 2 in there, I get a 0. Right? And if I pick 3, if I put 3 in there, 3 times 3 is 9. 9 minus 6, this will be radical 3. So 1, 2, 3. Radical 3 is 1 point some. So I know what the shape look like. Is in the domain x is bigger than or equal to 2, and is in the range y is bigger than or equal to 0. Remember what this says. The domain and the range must match. So this range should become this domain. If I restrict x to be bigger than or equal to 0, then I could label that as the inverse. And why is that? Because if you look at the graph of this, x squared over 3 plus 2 is a parabola that looks like this. If I am to restrict x to be positive, then guess what? That would be 1 to 1. And that's the one aspect that you have to get out of this more than anything. So without restricting this domain, I can't say that's an inverse. We want to do a bit more. You know what? Okay, I'll do one more of those. So if I look at number 36, I notice this is not 1 to 1. How do I know that? Because I know the graph of a parabola looks something like this. And that's definitely not 1 to 1, so no inverse exists. The condition was, if you recall, right, our definition was the inverse of a 1 to 1. The function must be 1 to 1. Otherwise, there's no way of doing that. Okay. And if I take this equation, now we're not going to graph this yet. We're going to graph everything in algebra, but this is 1 to 1. If I want to find the inverse, I switch x with y. I clear the fractions, which LCD is y, so multiply by y top and bottom. And that becomes xy equal 1 minus 8y. Get all the y's together. They both have a y. Factor that out. That's how you solve. And I will get, you know what, let me lower that just a bit more. And you will get, here, let me write that nicer. And you will get y to be 1 over x plus 8. Again, we will graph this in chapter 5, I believe. One more. Well, this is 1 to 1 because we know the graph of a cubic. How do you find an inverse? Switch x with y. And how do you solve a cubic? Isolate the cubic by itself. And cube root both sides. Square root is a problem. Cube root is not. I am going to pick another square root and do it. Just give me a sec. I couldn't find one. Let's make an example. Let's say f of x equals the square root of, what did we have there? Okay, let's say x plus 2. So if I want to find the inverse, I don't really need to graph it. I say, okay, that's 1 to 1. I know that. I could start by switching x with y. And when I want to get rid of the square root, I square both sides. That's when the problem happened. And I could say y equal x squared minus 2. But there's a problem. I know that's 1 to 1. I know the graph of this is a parabola shifted down 2 units. That's not 1 to 1. That's when I come in and say, you know what, let me find the domain of the original, or the range of the original. And to graph the original, I'm going to pick x and y. Where does the inside equal 0? When I put negative 2 in there, I get 0. If I move again, the domain is x plus 2 is bigger than or equal to 0. The domain is that x is bigger than or equal to negative 2. Now I need the range, because the range is going to become the restriction on the domain. Well, to graph it, that's how you figure the range. You say, all right, well, let's see. If x is bigger than or equal to -2, remember we go a point above. How about -1? Put a -1 there, that's 1. Square root of 1 is 1. So I get how the graph look like. The range is that y is bigger than or equal to 0. All what I have to do, add that and switch x with y. If x is bigger than or equal to 0, guess what? That will give me only the right half of the graph, which is 1 to 1. And now, the last aspect is really using this part. You have two options, and I'll allow you to use either. If you want to verify that two functions are inverses, you have two options. Either you do both of those, or you find the inverse of one and it shows the next. So they're asking, determine whether each pair of functions are inverses. Well, let's see if they are inverses. To figure out whether they are inverses, either find the inverse of that, show that it's this, or take f composite g of x and g composite f of x, and you want to show you're getting x in both cases. If one of those doesn't give you an x, you're done. This is f of g of x. G of x is actually right there. That is 3x minus 5 over 2. Now go to the f function. Wherever you see an x, plug that in. So that is twice. And in there, I'm going to put the entire 3x minus 5 over 2. Those cancel out. I'm left with 3x minus 5 plus 5 over 3. And I'm left with 3x over 3, which is x. It does check. Well, that's not enough. I still have to do all of this work. I have to do g of f of x. F of x is 2x plus 5 over 3, and it's right there. Now this says go to the g function. Wherever you see an x, plug that in. So if I replace that x by 2x plus 5 over 3, the 3's cancel out. I'm left with 2x plus 5 minus 5 over 2. Those cancel out. I'm left with 2x over 2, which is x. So yes, they are inverses. An alternative is for you to take one of those, switch x with y, and find the inverse. I'll accept that. That's fine. So it says determine whether those are inverses. How about problem number 20? Well, if I take f composite g of x, that is f of g of x. G of x is actually all of this. Now I'm going to go to the x and I'm going to put that right there. That is 1 over 2x plus 5. That is 1 over twice. And all what I'm going to do is replace this x by that mess. That is 1 over 2x plus 5. If I clean this up, that's 1 over 2 times 1/2 x plus, oh, those two cancel out. And those cancel out. And 1 over a fraction, 1 over a fraction is the reciprocal of this fraction. So it checks this way. That's not enough. I still have to take and g composite f of x. So I have to do it forward and backward. A lot of times it works one way and it doesn't work the other way. You'll be surprised. What is f of x? F of x is this mess. What is this saying? Go to the g function. There's g. I highlight that and register. Replace that x by this value. So the 1 over 2. In place of x, you're going to use 1 over 2 into x minus 5 plus 5. That's going to be, those two cancel out. 1 over a fraction is the reciprocal of the fraction. So the reciprocal of 1 over x minus 5 is x minus 5 over 1. And you notice those cancel out, and you are left with x. So yes, those are inverses. Now, the part I was talking about on number 14, if I was to take this, I'm giving you another option. If I am to switch x with y and solve for y, get rid of the fraction, subtract 5 from both sides, and divide by 2. So this is the inverse. So I'm giving you an option. You could take this, no, let's use green. You could take this and find its inverse and see if it matches this, and you say yes. That's an option I'm adding. You're allowed to do that if you like, whatever makes you happy. And there's the homework for this section.